In the pre-dawn stillness of the Utah desert, an object appeared. A pinpoint of incandescent light, a man-made star streaking across the final frontier between the void and our world. This was no ordinary meteor. This was a messenger carrying a precious cargo across an unfathomable gulf of space and time. Inside the descending capsule, protected from the fiery re-entry, lay a small canister, and inside that canister a handful of dark dust and rubble. It was a treasure more valuable than all the gold ever mined. A sample pristine and untouched for billions of years, plucked from the surface of a wandering world named Bennu. This celestial emissary had completed a 7-year, 4 billion-mile odyssey to touch an ancient asteroid and bring a piece of it home. The mission was called Osiris Rex, a name evoking Egyptian gods and the cycle of life, death, and rebirth. A fitting title for a quest seeking to answer the most profound question humanity has ever asked. Where did we come from? The dark grains now resting safely in a fortified cleanroom are not merely rocks, they are history. They are a library of cosmic information written in an atomic language that we are only just beginning to decipher. And the story they seem to be telling is one that could fundamentally reframe our entire understanding of our place in the universe. It is a narrative that suggests the very seeds of our existence, the chemical scaffolding of all life on Earth, were not forged here in some warm little pond. Instead, this chronicle hints that they were delivered from the heavens, hitching a ride on primordial relics just like Bennu. Could this handful of asteroidal dust contain the definitive proof that we are all of us, the children of the stars? The genesis of this extraordinary undertaking began decades ago, not in a spacecraft but in the minds of scientists. They dreamed of a mission that could perform a kind of cosmic archaeology, a voyage that could retrieve an untainted artifact from the solar system's formative eons. An ordinary meteorite, one that blazes through our atmosphere and crashes to the ground, is a compromised witness. Its fiery passage and its time spent on Earth's surface contaminates it with terrestrial biology and chemistry. It is like trying to study an ancient text that has been left out in the rain and scribbled on by 1,000 strangers. To get the real story, we had to go to the source. We needed a sample that had never known Earth's air, never felt its rain, never been touched by its life. We needed to intercept a time capsule in its native environment. The target chosen for this audacious retrieval was Bennu. Discovered in 1999, this minor planet is a near-Earth asteroid, its orbit bringing it tantalizingly close to our own. But its proximity was not its only appeal. Spectral analysis from ground-based telescopes suggested Bennu was a carbonaceous asteroid, a C-type. This class of celestial bodies is known to be rich in carbon, the fundamental element of all known life. They are believed to be some of the most primitive objects in our cosmic neighborhood, remnants from the swirling cloud of gas and dust that coalesced to form our sun and its planets more than 4.5 billion years in the past. Bennu wasn't just old, it was a fossil from before the beginning. It was a fragment of a much larger water-rich parent body that was shattered in a cataclysmic collision eons ago. This tiny world, only about 1/3 of a mile in diameter, has been wandering the solar system ever since. A lonely shard of a lost planet, preserving the chemical memory of our solar system's birth. The spacecraft designed for this mission, Osiris Rex, was a masterpiece of engineering. It was a robotic extension of human curiosity, equipped with cameras, spectrometers, and a sophisticated instrument for its most critical task. This was the touch-and-go sample acquisition mechanism, or TAGSAM, a robotic arm 11 feet long with a circular head at its end. The plan was not to land, but to perform a celestial kiss. A gentle 5-second touch to the surface, unleashing a puff of nitrogen gas to stir up regolith and capture the disturbed material in its collector head. It was a maneuver of breathtaking complexity and risk. After launching in 2016, Osiris Rex began its long, silent journey. It flew past our moon and a year later swung back by Earth, using our planet's gravity like a slingshot to catapult itself onto a trajectory that would intercept Bennu. In December of 2018, after traveling more than 1 billion miles, the spacecraft finally arrived at its destination. And immediately the mission faced a shocking surprise. The models, based on Earth-based observations, had painted a picture of a relatively smooth surface, a beach of fine-grained material. The reality was a treacherous, chaotic landscape. Bennu was not a sandy beach. It was a rugged, craggy world covered in enormous boulders. A spinning rubble pile barely held together by its own feeble gravity. The mission plan had called for a landing zone 50 meters in diameter. The science team now struggled to find any spot on the entire asteroid that was even a fraction of that size and free of hazards. A sense of profound anxiety settled over the team. The entire multi-year, near billion-dollar endeavor was now threatened by the very nature of the world it had come to explore. What followed was 2 years of the most detailed remote mapping ever conducted on a celestial body. OSIRIS-REx orbited Bennu closer than any spacecraft has ever orbited another world, at times just a mile above its boulder-strewn surface. It meticulously photographed, scanned, and analyzed every square inch, creating a map of such high resolution that a human could spot a coin on the ground if they were standing there. From this immense atlas of data, the team selected 4 potential sites, naming them after birds: osprey, kingfisher, sandpiper, and nightingale. After months of intense debate and further analysis, the final choice was made. Nightingale, a small crater just a few car lengths wide, hemmed in by menacing building-sized rocks. It was a high-risk, high-reward choice. The material in Nightingale seemed to be finer-grained, more promising, but the margin for error was terrifyingly small. A slight miscalculation in the final descent, and the spacecraft could be dashed against a jagged monolith nicknamed Mount Doom. On October 20th, 2020, the moment of truth arrived. From a control room on Earth, a signal was sent, a command that had traveled for more than 18 minutes at the speed of light to reach the distant automaton. OSIRIS-REx began its slow 4-hour descent. The spacecraft was now on its own. The time delay made real-time human intervention impossible. It had to navigate the final perilous meters using its own eyes and its own autonomous brain-matching features on the surface to the pristine maps stored in its memory. Tension in the control room was unbearable. Scientists and engineers who had dedicated years of their lives to this could only watch the telemetry data, helpless spectators to a drama unfolding 200 million miles away. The robotic arm extended, reaching out toward the ancient surface. The final seconds ticked by, then contact, a gentle bump, the TAGSAM head pressed against the dark regolith of Nightingale, a burst of nitrogen gas fired, a cloud of black dust and pebbles billowed up, funneling into the collection chamber. The spacecraft's thrusters fired, pushing it back away from the surface. The celestial kiss had lasted a mere 6 seconds. Success. A wave of elation and relief washed over the mission team. But the drama was not over. When the onboard camera imaged the collection head to confirm the sample, it revealed a new problem. The maneuver had been times 2 times successful. The head was so full of material that a small rock had become wedged in the mylar flap designed to seal it. Precious grains of primordial history were visibly leaking out into space. A race against time began. The team on Earth scrambled, jettisoning the original plan to spin the spacecraft to measure the sample's mass. They worked around the clock to command OSIRIS-REx to stow the sample head into its return capsule as quickly as possible. The maneuver worked. The leaking stopped. The priceless cargo was secured for its long voyage home. After another 2.5 years crossing the interplanetary void, that cargo finally landed in the Utah desert. It was transported to a specially constructed clean room at NASA's Johnson Space Center, a sanctuary designed to protect it from the contaminating influence of our own world. To comprehend the significance of what lay inside that canister, we must journey back not 7 years to the mission's launch, but over 4.5 billion years to the dawn of our solar system. Imagine a vast, spinning cloud of interstellar gas and dust, a cosmic nursery cold and diffuse. At its center, gravity begins to win. A protostar ignites our infant sun. The remaining material flattens into a colossal disk, a protoplanetary nebula. Within this disk, tiny grains of dust and ice begin to stick together. Electrostatic forces, then gravity, pull these motes into pebbles, the pebbles into boulders, the boulders into planetesimals. These planetesimals, the building blocks of planets, violently collide and merge, growing larger and larger. In the inner, warmer regions of the disk, rocky worlds like Earth, Mars, Venus, and Mercury are born. In the outer, colder regions, gas and ice giants like Jupiter and Saturn form. The asteroids, like Bennu's ancient parent body, are the leftovers. They are the material that never quite managed to form a full-fledged planet. They are frozen, pristine relics of that initial construction phase. Bennu's parent was likely a world hundreds of miles across, orbiting in the main asteroid belt between Mars and Jupiter. Critically, it formed in a region of the solar system where water ice could remain stable. Over millions of years, this water, heated by radioactive elements in the rock, would have melted. It would have percolated through the body of the asteroid, interacting with the rock and altering its chemistry. This process, known as aqueous alteration, created clay minerals that trap water molecules directly within their crystalline structure. It also concentrated and cooked the simple organic carbon compounds that were present in the initial nebula, transforming them into more complex and varied molecules. This celestial body became a kind of cosmic chemical factory. Then, perhaps 1 billion or 2 billion years ago, disaster struck. A high-speed collision with another large object shattered this world. The cataclysm sent fragments flying in all directions. One of those fragments was the collection of rocks and dust that would eventually, through its own weak gravity, reassemble into the rubble pile we call Bennu. For aeons, this small world has drifted a silent witness. Its orbit was eventually nudged by the gravitational influence of the giant planets, sending it on a new path into the inner solar system, where it would one day cross paths with our own planet, and with the curious machines we sent to meet it. Now let us turn our gaze to the early Earth. The world of 4 billion years ago was an alien planet. A hellish landscape of raging volcanoes, its surface a sea of molten rock, its atmosphere thick with toxic gases devoid of oxygen. It was a sterile, barren sphere, constantly bombarded by the leftover debris of planetary formation. There was almost no surface water. The intense heat of its formation had boiled away any initial inventory. And yet today our world is a blue marble, its surface 70% covered by vast liquid oceans. Oceans that are the crucible of all known biology. Where did all this water come from? And even more puzzling, where did the organic molecules come from? The complex carbon-based compounds that form the backbone of amino acids, proteins, and eventually DNA. For many years, the prevailing theory was that these ingredients were created right here on Earth. The famous Miller-Urey experiment in the 1,950 seconds showed that electrical sparks simulating lightning in a flask of gases, mimicking Earth's early atmosphere, could spontaneously form simple amino acids. It was a landmark discovery suggesting life could arise from non-life, a process known as abiogenesis. But there was always a problem. The conditions on the early Earth were incredibly violent. The constant volcanic activity, the relentless bombardment, the searing ultraviolet radiation from a young sun unfiltered by an ozone layer. This environment would have been just as effective at destroying complex molecules as it was at creating them. It was a difficult, perhaps impossible cradle for life's delicate beginnings. This is where Bennu and its kin enter the story. The analysis of the samples began with a surprise even before the main canister was opened. When the science team examined the exterior of the Tagsam head, they found it was coated in fine black dust, material that had clung to the device during the collection event. This initial bonus sample was the first to be studied, and what it revealed was stunning. Using advanced techniques like scanning electron microscopy and X-ray diffraction, the scientists found that the dark grains were rich in two key things. First, water. Not liquid water, but water locked away inside. The molecular structure of clay minerals, just as predicted. The very chemistry of the rocks confirmed they were formed in a water-rich environment. This was the smoking gun evidence that asteroids like Bennu are carrying vast quantities of water across the solar system. Second, the sample was absolutely loaded with carbon, up to 5% by weight in the form of complex organic compounds. And critically, they also discovered phosphates. Phosphorus is the P in ATP, the molecule that carries energy in all our cells. It forms the structural backbone of our very DNA. Its presence is absolutely essential for life as we know it. So here it was. In a single tiny sample of extraterrestrial rock, we had found the three most critical ingredients for biology: water complex, organic molecules, and phosphates. All the essential building blocks for life present in abundance on an object that predates the stable formation of our own planet. To grasp the magnitude of this discovery, imagine you are a master chef trying to bake the most complex cake imaginable, the cake of life. You find yourself in a vast, chaotic kitchen, the early Earth. The kitchen is on fire, prone to explosions, and you have only the most basic ingredients available, like flour and salt. You might, with incredible luck, and over an immense period of time, figure out how to synthesize a few more complex ingredients like sugar or eggs from the raw materials at hand, but it would be a slow, arduous, and constantly interrupted process. Now imagine that while you are toiling in this chaotic kitchen, a fleet of delivery trucks starts arriving. These are the asteroids and comets. Each truck, like Bennu, pulls up and unloads a perfectly prepared gourmet ingredient kit. One truck delivers pre-packaged high-quality water. Another delivers a vast assortment of sugars and complex carbohydrates, the organic molecules. A third truck delivers the essential minerals and flavorings, the phosphates. Suddenly, your job as the chef is transformed. You are no longer struggling to create the ingredients from scratch in a hostile environment. Instead, you are simply presented with a pantry full of high-quality pre-made components. All you need to do is figure out the recipe for combining them. The delivery of these cosmic building blocks doesn't solve the final mystery of how lifetimes ignited times, but it makes the process immeasurably more probable. It changes the problem from one of improbable creation to one of inevitable assembly. The idea that life's ingredients, or even life itself, came from space is not new. It is an ancient concept known as panspermia, from the Greek words meaning all seeds. The Greek philosopher Anaxagoras, in the 5th century BC, speculated that the seeds of life were spread throughout the cosmos. In the modern era, this hypothesis was championed by astronomers like Fred Hoyle and Chandra Wickramasinghe. They argued that interstellar dust clouds contain not just organic molecules, but even preserved bacteria and viruses, which then rained down on fertile planets like Earth. For decades, their ideas were considered fringe, even pseudo-scientific, by the mainstream biological community. The paradigm began to shift in 1969. That year, a massive fireball lit up the skies over the small town of Murchison, Australia. A meteorite had exploded in the atmosphere, showering the area with hundreds of pounds of dark, carbon-rich rock. The Murchison meteorite became one of the most studied in history. When scientists analyzed its fragments, they found something revolutionary. The rock contained dozens of different amino acids, the building blocks of proteins. Some were common to life on Earth, but many were not. This proved they were not terrestrial contamination. They had genuinely formed in space inside the meteorite's parent body and had survived the violent journey to Earth. Murchison made panspermia respectable. It was the first hard evidence that the chemical precursors to life were not unique to our planet. But Murchison, for all its importance, was still a compromised sample. The Bennu material is different. It is pristine. It is a direct line to the chemistry of the early solar system, unfiltered, unweathered, and uncontaminated by Earth. It provides a far clearer and more definitive picture. The initial findings from Bennu don't just echo the Murchison results, they amplify them on a grand scale. The evidence now allows us to paint a vivid new picture of our planet's youth. We see a young Earth between 4.1 and 3.8 billion years ago. This era is known as the Late Heavy Bombardment. The solar system was still a messy, chaotic place. The gravitational dances of the giant planets had unsettled the orbits of countless asteroids and comets, sending a torrent of them careening into the inner solar system. The sky of this primordial Earth would have been a terrifying spectacle, a ceaseless rain of fire. Impacts far larger than the one that wiped out the dinosaurs were a daily occurrence. The surface of our world was being constantly reshaped, melted, and vaporized. It seems like the worst possible environment for life to begin. But the Bennu findings ask us to see this violence in a new light. This bombardment was not just an agent of destruction, it was an agent of creation. Every asteroid like Bennu, every comet that crashed into our planet was not just delivering devastation, it was delivering a payload of water. It was delivering a rich inventory of complex organic chemicals. It was delivering the phosphates needed for metabolism and genetics. This cosmic deluge was seeding the nascent oceans. It was creating a planetary-scale chemical soup rich with all the necessary precursors for life. The very cataclysm that made Earth's surface seem so inhospitable was simultaneously providing the exact ingredients needed for biology to emerge from chemistry. This does not mean that abiogenesis on Earth was impossible. Perhaps life's building blocks were being formed in deep-sea hydrothermal vents, or created by lightning in the atmosphere times and times being delivered from space. But the sheer quantity of material implied by the Bennu sample composition suggests that the cosmic delivery mechanism was not just a minor contributor. It may well have been the dominant primary source of the organic material that kick-started all life on our world. The work on the Bennu samples has only just begun. Scientists will be studying these precious grains for decades to come. They will search for more and more complex molecules. They will analyze the isotopic ratios, the atomic fingerprints that can tell them exactly where and how these elements were forged. One of the most exciting avenues of research will be the search for chirality. Many organic molecules, including amino acids, can exist in two forms that are mirror images of each other, like a left and a right hand. Life on Earth, for reasons we still don't understand, exclusively uses left-handed amino acids and right-handed sugars. If the Bennu sample shows a slight preference for one-handedness over the other, it could suggest that this fundamental bias of life was itself inherited from space. It would be a clue that the very architecture of our biology was determined billions of years ago in the watery interior of a now shattered world. The OSIRIS-REx mission does not exist in a vacuum. Japan's space agency, JAXA, conducted a similar mission called Hayabusa 2, which returned samples from another carbonaceous asteroid, Ryugu. Their findings have been remarkably similar to NASA's, confirming the presence of water amino acids and even nucleobases, the letters of the genetic code. Together, these missions are building an overwhelming case. This is a golden age of solar system exploration. Missions are underway to visit metallic asteroids, Trojan asteroids, and to bring back even more samples from different classes of objects. Each one will add another chapter to this emerging story of our origins. The implications of this extend far beyond our own planet. If the building blocks of life are not a rare terrestrial fluke, but are instead common, ubiquitous components of asteroids that are spread throughout the galaxy, then the probability of life emerging elsewhere skyrockets. The universe, it seems, is predisposed to life. The cosmos is generously seeding every nascent planetary system with the necessary ingredients. It means that wherever there is a rocky planet in a stable orbit with liquid water on its surface, it is almost certain that it received the same cosmic ingredient kit that Earth did. The question of whether we are alone is transformed. It shifts from how could life possibly start to how could it possibly not. From a dark speck of dust in the Utah desert, a new perspective emerges. We look up at the night sky at the shooting stars, and we see them not just as beautiful streaks of light, but as our potential ancestors. We see the asteroids not as menacing threats, but as the cosmic gardeners who may have planted the first seeds in our world's primordial soil. The journey of OSIRIS-REx is a testament to human ingenuity, patience, and our insatiable desire to understand our own existence. It is a story that connects the largest scales of the cosmos with the smallest scales of our own biology. The atoms in our bodies, the carbon, the nitrogen, the oxygen, were forged in the hearts of dying stars billions of years ago. We have long known that we are made of stardust, but now we are beginning to understand the incredible journey that material took to get here. It was gathered into asteroids, processed in watery interiors, delivered to a young Earth, and from that celestial inheritance through a 4 billion year saga of evolution, it has produced consciousness. A consciousness that can now build machines to travel back out into the cosmos, to retrieve a piece of its own ancestral history, and to finally read the story of its own beginning. The black dust from Bennu is not just a rock, it is a mirror. And in it, for the first time, we are seeing a clear reflection of our own cosmic origins.